Hi everyone, in this video we're going to be starting the comparison tests, or section 11.4 in the textbook. So in this section we're going to be learning two new tests for some positive term series, which are going to be the direct comparison test and a limit comparison test. So our main idea is going to be that if a series is hard to understand by itself, we can compare it to a simpler series that we already know. So our big question is, what known series does this one behave like and why? And now, these are going to be the series we're going to be comparing it to. So these are we call them the benchmark series. So before we start the new test, let's remind ourselves of the two main benchmark series. So the first one is a P series with 1 over n to the P, where the series converges if your P value is greater than 1, and it diverges if your P value is less than or equal to 1. So this is useful because many complicated fractions simplify to something that behaves like 1 over n to the P, or the P series. And then the next series we're going to be comparing it to is the geometric series. So this can take the form of a plus ar squared plus ar cubed all the way, with a being the first term and r being the common ratio, or you can just use the series notation. And we know that this series converges if the absolute value of r is less than 1, and it diverges if the absolute value of r is greater than or equal to 1. And this one is useful because some series are built by multiplying the same number over and over, so we can naturally just compare them to a geometric series. Now, let's talk about our first test. So this is called the direct comparison test. And so for this one, we're going to suppose that 0 is less than or equal to a sub n, which is less than or equal to b sub n. So this basically means that a sub n is going to be the smaller term, and b sub n is going to be the bigger term. Now, if the bigger series, b sub n, converges, then the smaller series, a sub n, also converges. So why does this make sense? So we know that the a sub n, or the smaller term, is never larger than b sub n. So if the larger pieces are if the larger pieces are already going to add up to like a finite number, or it's already going to converge, then we know the smaller pieces are also going to add up to a finite number, or they're also going to converge. So an easy way to think about this is smaller than the convergence series basically means convergent. So now we have our second one, which is for proving divergence. So say you have 0 is less than or equal to b sub n, which is less than or equal to a sub n. So this means that in this case that b sub n is going to be the smaller term and a sub n is going to be the bigger term. So if the smaller series b sub n already diverges, then the bigger series a sub n must also diverge. So why does this one make sense? So we know that a sub n is always at least as large as b sub n. So even if the smaller pieces already add up too much and they diverge, then the bigger pieces are also going to diverge, right? They're not just suddenly going to converge. So a way to think about it is bigger than a divergent series equal divergent. So if you think about it, bigger starts with b, and we're looking at b sub n, right? The smaller term, so b sub n bigger. I don't know if that helps. I don't know what that memory pattern is called, but if it helps memorize the what's it called? If it helps you memorize what to do, then I guess it works. So now we're going to talk about the limit comparison test. So this one's pretty easy. So basically, it's just saying that if we know what a series behaves like, and using inequality is awkward, we can just take the ratio of both of them and use a limit comparison test. So I guess the textbook definition is that if two positive terms are the same size for large n, then their series should also behave the same way. So I guess the whole idea is basically that instead of like asking which one is bigger, like which series is bigger, instead of comparing them, we're going to think about the ratio. So does the ratio of the between them approach a positive finite number? And if they do, then they're basically the same size. So I guess you can say the math version of this is that if you have a term a sub n, which is greater than 0, and b sub n, which is also greater than 0, and the limit of the two terms a sub n over b sub n equals c, where c is a value between 0 and infinity, then we say that both a sub n and b sub n are either going to converge or they're going to diverge. So that's basically a limit comparison test. So now let's see when to use what test. So I guess a good strategy is that you use the direct comparison test when you can write a clean inequality. I guess that's like straightforward, right? Nothing like too fancy or complicated. And then we can use the limit comparison test when the terms are like messy, but the end behavior is going to be the same for long term. So that was a lot of definition and like just talking. So now let's actually do some examples and hopefully they help. So example 1. Determine whether the series 1 over n squared plus 1 converges or diverges. So I'm going to give you like 2-3 seconds. I want you to think about what you just learned, and I want you to I want you to identify what type of test we're going to use here. Alright, it's been like what, 2-3 seconds. So in this example, if you guess we're going to be using the limit comparison test, you're wrong, because we actually use a direct comparison test here. So why do we use direct comparison test? So if you think about it, let's look at this term we have. 1 over n squared plus 1. So what is this term like? What is a series that you can compare this to that looks really close? Well, to me, this basically looks like 1 over n squared, right? So we know that 1 over n squared plus 1 looks really similar to 1 over n squared. So the reason we use the direct comparison test is because we can compare these with a really easy inequality. And we know that 1 over n squared is a p-series term, which we talked about in the beginning of the video, that we're going to be comparing all of our series to either a p-series test or geometric. So it worked out for us. So let's choose our benchmark series now, which I already told you what it was. So let's write our first term, a sub n. So that's just the 1 over n squared plus 1, the series we had in the problem. Now let's choose our b sub n, which is going to be, we'll say it's 1 over n squared. So we chose 1 over n squared because we know it's a p-series term, so it's easier to compare to. So we know that the series for 1 over n squared, so we know that this is a p-test series, as we talked about. So if you remember, our p value in this case is 2, right? It's 1 over n to the p. So in this case, our p value right here is 2. So we know that since p is equal to 2, and we know that 2 is greater than 1, which is our condition for the p series, we know that this converges. Therefore, you can write that this series converges. Okay, my handwriting might be messy, but we'll explain this a little bit as we go on. So now, let's compare the terms. So we know that n squared plus 1 is greater than n squared. Now if we're asking why didn't write the 1 over, like 1 over n squared plus 1 is greater than 1 over n squared, it's because the fractions are easier to deal with. So we know that. So why is this going to be useful? Well, we know that both quantities are positive, and when we take the reciprocals of them, the inequality reverses. So if you take the reciprocal, so basically just putting 1 over 1, okay, 1 over n squared plus 1 is less than 1 over n squared. So I'll explain why we left this one right here as just n squared plus 1 is greater than n squared in a few seconds. So now, after we did the reciprocal, right, and we got the 1 over n squared plus 1 is less than 1 over n squared. Oh yeah, also when you take the reciprocal, the inequality flips. So now, this is like our direct comparison test, right? We had 0 is less than or equal to a sub n, which is less than or equal to b sub n. So that's why I wrote it like this, because we wanted for the test to work, the condition was that if b sub n converges, then a sub n converges. So writing like this, I could flip it, right? Putting the 1 over n squared when we took the reciprocal. Now we said that 1 over n squared is greater than 1 over n squared plus 1, which satisfies this condition for the direct comparison test. So now all we gotta do is just apply the test. So we already know from we did example bottom here, and the bottom right here, bottom left, so the series of b sub n is equal to just 1 over n squared, which we already showed that this converges. So we can just say that so I'm trying to think of how to write the answer. Okay, so well, I guess we didn't finish. So since we know that b sub n, the 1 over n squared, converges, so by the direct comparison test, we know that a smaller series, a sub n, also converges, so we don't have to solve it. Therefore, our final answer, I guess, what you could write out is like this. So right from n equals 1 to infinity of 1 over n squared plus 1 converges by the direct comparison test. So basically all you want to do is you want to look at the series. You want to see that if there's something really close you can compare it to. In this case, we got lucky that there was a plus 1. So you can compare it to 1 over n squared. But also, when you choose something to compare to, you want to make sure it looks like a p series or a geometric series. Right? You want to compare it because those are the easiest ones to identify the end behavior. So basically, all we want to do is, we want to find the easy series that we already know, if it converges or diverges, and just compare that to our original series, so we don't have to do any work. And then I guess the only difficult part of these type of things is identifying the test to use and maybe finding the series to compare it to. So I guess that's the hardest things, and maybe memorizing the formula too, I guess, or the theorems, I guess. So we have our final example that 1 over n squared plus 1, oh, I'm sorry for the writing, converges by the direct comparison test. Now, let's move to our second example. We have determine whether n over n cubed plus 1 converges or diverges. So I'll give you, again, 5 seconds to think which test we would use here. So if you said we would use the limit comparison test, you are correct. Didn't trick you this time. So why do we use the limit comparison test here? So in this case, our term is n, whoops, didn't mean to write it in blue. We have n over n cubed plus 1. I'm sorry, just ignore my 3 word writing. It's terrible. So we have n over n cubed, right? So we know that when n gets very large, that our most important parts of the fraction are going to be the highest power terms, right? So as we plug in numbers close to infinity, this plus 1 right here isn't going to do shit. It's not going to like be a big deal breaker like, oh, it's going to be like infinity over infinity plus 1. Like the plus 1's not going to matter at all. Like, so therefore, we just look at the highest power terms. So in this case, we have in the numerator it's going to be n, and the bottom is just going to be what? N cubed, right? So we can say that n over n cubed plus 1 should behave basically like n over n cubed for large n values. Now if we simplify this, so n over n cubed, you know, this is like a imaginary one, right? We just don't write it because it's like given, like n, like any variable is always or is just a variable to the first power. So we know that this is just equal to 1 over n squared. Why? Because if you remember, when you divide like, so we have n forward over n squared, dividing like two terms with the exponent is like subtracting them, right? So it's like this would be equal to just n squared because 4 minus 2 is 2. So in the other case, it's like 1 over 3, right? So 1 minus 3 is negative 2. So n to negative 2 can also be rewritten as 1 over n squared to make the exponent positive. So that's why n over n cubed is basically 1 over n squared. So basically all we did, right? We looked at the n behavior. We look as we plug in infinity. We know the plus 1 doesn't matter. The only thing that matters is the large values, right? So we simplified from n over n cubed plus 1 to n over n cubed. And we know we could compare that to 1 over n squared. And funny enough, that's the same p series we used last example. So I guess coincidentally that worked out as well. So basically all we did was we looked at the dominant terms, right? And we asked ourselves what the fraction behaves like when n is really large. And because the expression was kind of messy, the limit comparison test would be more natural to use in direct comparison. So now let's choose our term. So we have a sub n. It's going to be equal to just our series right here, n over n cubed plus 1. We have b sub n. It's going to be the one we're comparing it to, which is 1 over n squared. Now, we know that the 1 over n squared series converges because it's a p series with p equals 2. But we're not using direct comparison test, right? We're doing limit comparison test for this one. So now we have to form the ratio. So if you remember, the ratio is the limit as n approaches infinity of a sub n over b sub n, which equals c value. So now we just plug our series in. So we have limit as n approaches infinity of n over n cubed plus 1 over 1 over n squared. Now you're going to be like, this does not look easier, but basically, so for this problems, these are problems when you use a limit comparison test, you're always going to multiply the bottom by reciprocal, right? So the 1 over n squared, you multiply by n squared at top, right, to simplify this. So if you really want to, you don't have to, like, when you do the limit, the a sub n over b sub n, you don't really have to do both of them dividing. You can just go ahead and just do, like, the top series multiplied by reciprocal at the bottom, if you get comfortable and to save more time, I guess. So that's all you're going to be basically doing. So in this case, we just multiply the bottom by n squared. We cancel this out, right? So this becomes the limit of n approaches infinity of, well, n squared times n is just n cubed. So it's just going to be n cubed over the same thing on the bottom, n cubed over n cubed plus 1. So now, let's rewrite this as limit as n approaches infinity of n cubed over n cubed plus 1. So we can divide both the top and bottom by n cubed, simplify. So we divide each term on top and bottom by n cubed. So we're going to get the limit is n approaches infinity. So we know that n cubed divided by n cubed is just 1. Same thing on the bottom. n cubed divided by n cubed is also 1. And then 1 divided by n cubed is just 1 over n cubed. Now we can plug in infinity. So when the top is the same, it's going to be 1 over 1 plus, remember, when you plug infinity to the bottom, that's plus 1 over infinity cubed. And we know that a super big term divided by a small term, or sorry, a small term divided by a super big term is basically 0. So this is basically just 1 plus 0. It's just going to be equal to 1. Therefore, we get that. I'm going to move these to the top really quick. So we know that so we got our ratio right, that a sub n over b sub n to be equal to 1. And we know that the limit is 1 and 1 is a positive and finite value, right? Therefore, since we know that our series b sub n, 1 over n squared, converges, and the original series also converges. Therefore, oh, I'm sorry. Also, before I explain that we know that the c value in this case had to be this. It was the c just had to be between 0 and infinity, and we know 1 is between 0 and infinity. So we know that by that, this both of the series converges. Remember the condition, or sorry, not the condition, but the limit comparison test, that if the limit of your two terms equaled a value that was between 0 and infinity, then either both of them converged or diverged. So in this case, our limit, or the ratio, was equal to 1, and we know 1 is between 0 and infinity. So we know that both of these converge. And why doesn't it converge? Because we know that it's the p series, right? Our b sub n was 1 over n squared, and we know that this converges when p is greater than 1. Therefore, the original series also converges. So we can say that this series converges by the limit comparison test. So now let's go to a recap. So basically, the main points for this video was that both of these comparison tests are for positive term series, and the direct comparison test is best for when you can write a clean inequality, and the limit comparison test is best when you can explain what the term behaves like for large n. So I guess another thing, that when you use the direct comparison test, make sure you keep track of which series is smaller and which one is bigger. And most of the time you're going to be comparing this to the p series or a geometric series. So hope that helped. Thank you for watching and have a good day.